Energy conversions in motors and generators. There is a difference between a motor and a generator. As I told you, electrodynamics studies the relationship between electricity, magnetism, and mechanical, which is like movement phenomena. We do generators and motors. This is a question that they can ask you in your test or in your exam. What is the energy conversion that takes place in motors and generators? When you see the words energy conversion, convert means to change. So we're changing one type of energy into another type of energy. And motors, electrical motors, they transform electrical energy into mechanical energy. Electrical generators do the opposite. They transfer mechanical energy into electrical energy. Going into the difference between motors and generators. How do I recognize that the thing on the left is a motor, the thing on the right is a generator? You need to look at the diagram. You can see that they both have magnets. So north, south, that's a magnet. North, south, over there. They both have a coil or an armature, which we'll speak about later. That's coil. That's this conducting wire that's bent into a coil. They both have it. The pictures look different, but they both have it. They both have in these diagrams, they both have what we call a split ring. I'll explain what that is later. So what is the difference? The motor has this, a power source. That makes sense. A motor has a battery or an AC power source. Remember, with motors, we give it power, we give it electricity. We give it electricity. And what it does with that electricity is it causes this thing to spin. It converts it into mechanical energy. That is the point of a motor. So when we see a motor, you will see a power source. So you'll see a battery like that, or they could do the battery like that, or they could give you an AC power source, which is illustrated by that symbol. Just by the way, that's an AC power source. Other machine that we'll be talking about, let's zoom in on this one. We have over here for this machine, again, a magnet. We have an armature or a coil over there that the current travels through. We have the split ring, same. But what is different here is, do you see over here, I do not have a battery. I do not have a power source. What I have instead is, in this case, it's a voltmeter, but it doesn't have to be a voltmeter. It can be an ammeter, it can be a galvanometer, it can be something that measures current or voltage, or it could even be a light bulb, or it could be an appliance, so something that uses power. We're going to start off with motors, but like I said, motors, spoke about the energy conversion, they are both based on the motor effect. So if the question says, name the principle that the motor operates on, name the principle that the motor operates on, you will say that it operates on the motor effect, or it's based on the motor effect. And this is what the motor effect says. This is, again, something that we should have covered in grade 11, or you should have done in grade 11. A current carrying conductor. What that means is a wire that carries current. If I place that current carrying conductor, so a coil or a wire that has current running through it, if I put that thing in another magnetic field, what happens is it experiences a force. So it'll start to move. It's quite crazy that this happens, but basically, you see here we've got magnets. This is the current carrying conductor. The direction of the current, according to this diagram, is this way. What basically happens is the current carrying conductor, if a conductor has current that's flowing through it, what we cannot see with our eyes, but what exists is that because there's current flowing through the conductor, that current creates a magnetic field. Okay? So the wire creates a magnetic field. That magnetic field interacts with the magnets that you see on the screen over there. So the current in the wire creates one magnetic field. That magnetic field interacts with the other magnetic field. So it's two magnetic fields interacting. And what that causes is a force. A force on the wire causes the wire to move. The wire will move up or down. It's pretty cool. That's the motor effect. And I just wrote everything I said over there for you as a note so you can remember. And we can use our left hand. It's called Fleming's left-hand motor rule to determine the direction of the force. Okay, so what I want you all to do is, oh, and just before we do this, motors work on conventional current. So remember I told you it's electrical energy to mechanical energy, so current is flowing. We work with current that flows from the positive terminal of the battery. Remember, if you have a battery like that, the positive terminal is the long one. The negative terminal is the short one. So we work with conventional current that flows from the positive terminal to the negative terminal. So the current is flowing this way. What I want everyone to do is we're going to use our hands. So if you've done this in class, this is a familiar thing. This is not something that's new. It feels a bit weird, but you need to use your hands like this. I'm just looking at my camera to make sure that my hands look right. So my fingers need to be at 90 degrees to each other. So it's like you're doing this, but then your middle finger goes out like that. That's how our hands are. And our hands, we're going to use our left hand. Let me just see on the camera right now. That looked like my right hand, but it's because my camera is flipping me. Okay, this is my left hand. My camera is mirroring me. You use your left hand, and this is what the fingers mean. Okay, let's go through it. Your thumb, your first finger, which is your thumb, your first finger represents the force. Okay, what I mean by force is, will the wire move up? If your thumb is pointing up, the wire will move up. If your thumb is pointing down, the wire will move down. Your second finger, this pointer finger here, they call it B on this diagram. I don't like to refer to it as B. It's a bit confusing. It is the magnetic field finger. Magnetic field. So you always point towards the south. Okay, towards the south. I will show you with lots of examples, so don't worry. You point towards the south. Then this third finger is your current finger. It points in the direction of the current. Remember, conventional current from positive to negative terminal of the battery. How I was taught it is how I remember the rule. It's the father, mother, child rule. Okay, it sounds silly, but it's like a little family. The father is the first finger. It represents the force. The mother is the magnetic field finger. Okay, it points towards the south. The child fingers, child starts with a C, is the current finger. It points in the direction that the current flows. Okay, so I hope you all have your left hands out because we're using them for this lesson. This is a diagram that I found on the internet. I think it's quite helpful. So what you're going to do in order to figure out which way this wire would move, you use your left hand. So you point your mother finger, your magnetic field finger. Magnetic field points from the north to the south. So can you see how this person's finger is pointing towards the south? Then they tell you that the current is flowing in this direction. You can see indicated by this arrow over here. That's why the middle finger of this person, the current finger, is pointing sort of like out of the screen, if that makes sense. It's pointing like, if you had to do it right now, your middle finger should be pointing towards you. Your thumb is pointing up. What that means is that that wire will move up. And it's this principle that motors are based on. Okay, here's another one. If the first one was unclear, okay, you can see it kind of like trying to draw it in 3D, which is a little bit helpful. So just like we can do this rule or apply this rule to a single wire, we can apply to a motor where the wire is bent into a coil. So can you see here? It's bent like that. Okay. So we can apply the rule to the coil, which we will do in a second. Okay, let me just check on everybody. Is everybody okay? I don't see any questions and I don't see any hands. I think we're fine. Okay, awesome. Remember, you're allowed to ask me, hey? Thank you. Awesome. Cool. Let's carry on. Some things that you could be asked in the exam, additional things, is What affects the power of an electric motor? So how can we increase the force on the motor? And we can increase the magnetic force that turns the coil by increasing the strength of the magnets. We use stronger magnets because think about it. If the magnets are stronger, if these things are stronger, the magnetic field is stronger. So the two magnetic fields that interact with each other will produce a stronger force. We can increase the current strength. Okay, increase current strength. Stronger current will mean a bigger force. We can increase the number of turns in the coil. This is again something that we learned last year. It's just about how many times the wire is turned around each other. Okay, don't worry too much about that. If you don't understand it 100%, it's okay. This is theory. You can learn it. Before I go into practicing the left-hand rule with you, I want to speak about the different components of the motor. So we've got what they call the armature, which is the coil. It's this thing over here is the armature. Okay. And I actually do have, I'll show you here, I have a slide coming up a little bit later about all the components. And I know it says components of a generator, but the functions that they have are very similar. Okay, so I will also send you those slides, but for now, armature, I just want you to know what the things are. This is the armature. Obviously, we have our magnets. Just before we speak about using our left hand because I want us to practice. I want to speak about AC motors and DC motors. So if you haven't heard the words AC and DC, AC stands for alternating currents. Alternating current. So alternating means that it's changing. And then DC stands for direct current. It means that it flows in one direction. It does not change. It's direct. Okay, so alternating, the current changes. Direct, it stays in one direction. If we have an AC motor, and this is also true for generators, so keep this in mind. If we have an AC motor, motors uses slip rings, and slip rings look like this. There's two of them, and they slip onto the ends of the coil. So it's not obvious, but the first slip ring, this one over here, is connected to, let's actually highlight it. This first ring over here is connected to this side of the coil. Okay. And this slip ring is connected. I think someone's mic is unmuted. Please just make sure your mics are muted for me. If you're not answering a question or asking a question, happens. Okay. So the bottom slip ring is connected to the other side of the coil. Anyway, what happens is those rings rotate with the coil and then they make contact with the brushes. The brushes don't rotate with the coil. They stay in a fixed position and the rings go like this around them. Hope that makes sense. There are some really great YouTube animations that go through motors and generators, and it's really, really nice to visualize it. So I can't show you how it looks visually because I just have these static images, but I will share the YouTube links that I found that I play for my classes, and it's really, really helpful to see it moving in in real time, the little animations. It really, really helps. Okay, cool. So that is the AC motor. So all I want you to know, grade 12s, is that AC motors uses slip rings, and AC motors uses an AC power source. DC motors, DC power source like a battery, and they have a split ring. So a split ring is one ring that is split in the middle. You can clearly see the difference between the two of them. Okay, what I want us to practice now, and I need to switch my camera over to this overhead camera that I'm using. So we can give you something like this in your exam. A simplified diagram of an electrical machine is shown below. First things first, and actually I'm going to do this question with you after I do a little bit of this hand stuff with you. The first question they would ask is, do you see how they don't actually say that it's a generator or a motor? I cut off the questions because I just want to focus on using our hand. But the first question would be, Is it a generator or is it a motor? And how do we know?
Yes, ma'am, it's me.
Yes, tell me what you think.
A motor, ma'am, because
Yes,
the battery.
100%. Beautiful. Okay, well done to everybody. I'm sure a lot of you were seeing that. So what we see is electrical machine. Remember, generators also have the magnets. Generators also have the coils. This split ring tells me that it is DC, but it could be a DC generator or DC motor. So the thing that's telling me that it's a motor, a DC motor to be precise, is this little guy over here, the battery. So we don't see a voltmeter. Yes, I see someone said we don't see a voltmeter. We don't see a handle to turn this thing. We don't see a light bulb, but we do see a battery. So the important thing here, if they had to ask you, is you would say that there is a power source. Because remember, motors convert, they use a power source to convert electrical energy to mechanical energy. So we need to see a power source. Right, now, what we're going to do, and what I want you to tell me, now listen carefully, this is my motor, okay? You're going to use your left hand, remember, left hand like this. And what you're going to do for me is you're going to tell me which way this coil will turn. Will it turn anti-clockwise or will it turn clockwise? Okay, I'm going to let you think about it for a second. Just so we're all clear on this, when I do it with my matrics in class, like I have to physically demonstrate because it's very difficult. Okay, this is the back of my calculator. We're just going to go with this. If this is the coil, turning clockwise would be like this. Okay, like that. That would be clockwise, that way. Anti-clockwise would be like the other way. Okay, the reason why is because a clock goes like this, obviously. You know how a clock goes. A clock goes like this. So clockwise would be this thing turning like this, and anti-clockwise would be it turning like this. Up.
Yes, ma'am.
Yes,
I think it's anti-clockwise.
I think I agree with you. I think I agree with you. Who else thinks it's anti-clockwise? Hey, Luto, you think it's anti-clockwise? Or do you have a question? Okay, let's go over this. Okay, this is not completely obvious. And I know when I did this with my class the other day, we took a little bit of time to get this right. So I want to make sure we get it right. Then when we move on to generators, which is the other hand, it will be much easier. Okay, so what we do is you use your left hand, you put your fingers like this. Okay, so it's like these two fingers are at 90 degrees, and then you pop out your middle finger like this. What you need to do, because this is a motor, is we know the easiest finger, actually, let's start there. The easiest finger to figure out is the mother finger, the magnetic field finger, because that needs to point to to point from the north to the south. So you go like this. Okay, I'm not saying that my hand is in the correct position yet. I'm just saying that this finger is correct. This finger must point from the north to the south. Okay, then, and this is the difficult part, grade 12s, so try and focus and see what I mean when I say this. The next part that you need to know, the next thing that you need to do is you need to consider which way the current is moving. Remember we said that we're working on conventional current. So conventional current flows from the positive terminal of the battery, which is this long one over here, to the negative terminal of the battery, which is this one over here. So current goes this way. Watch what I'm doing. The current goes like this, then like this, then like this, and then it goes into the coil here. Okay, so the current in this branch, focus on what I'm saying, it's this branch that I'm looking at. The current in that branch is going like that. Okay, because it goes from the positive, like that, to the negative. So in this branch, it'll go down. Okay, that's the first thing. When you decide which way this thing is turning or how to know which way it's turning, you need to focus on one of these branches. We're not going to look at both. It's going to confuse us. We're going to look at one of the branches at a time. So I'm going to focus on this branch, the pink branch, I'm going to call it. So we point with our mother finger, our magnetic field finger, towards the south. This finger, this is the current going that way. It's not going this way, it's going that way. So what you need to do is you need to take your current finger and you need to point it that way. Okay? You need to do some twisting of your hand here. It's quite uncomfortable actually in some cases. But what you're doing, and I hope you can see, is my thumb is pointing down. My magnetic field finger is pointing to the north, and my current finger is pointing that way. What's my thumb doing? I just said it. My thumb is pointing down. Now think about it logically, and this is where I'm going to use a prop to represent the coil. This is the pink branch. This is the pink branch. Okay, the pink branch is on the left. It's here. If this is going down, which way is this thing rotating? It's rotating anti-clockwise. Okay, I hope you understand it. Let me just show you with the other branch to show you that it makes sense. Let's look at the other branch, the green branch. If I ask you which way the coil is rotating and you look at the green branch, you come to the same conclusion. Use your left hand. Your second finger, your mother finger, must point to the south of the magnet. But in this case, your current finger, which is this finger, must point down because I'm looking at the green branch and current is coming down. For the green branch, which way is the green branch turning? Which way is my thumb pointing? It's pointing up, which means that the green branch is going up. So the green branch is going up, the pink branch is going down, which makes it turn anti-clockwise. Okay, I hope that that's clear. Please let me know if you want me to do another one with you. Is part of this because the answer's on you. Scratching it out. Sorry. It's telling me which way it's turning. Okay. Here's the second one. I'll give you a second. Okay. What do we think, everybody? Yes, I'm seeing things in the chat that I'm liking. It is clockwise. Well done. Well done, everybody. Okay, let me explain for the people that may not have gotten there. So, again, north to south. So in this case, the north and south are in the same position. Please note, grade 12s, that they might swap these. It's not always that the north is here and the south is here. Okay, but in this case it is. So your finger points to the south. But what's different in this one is that the battery is different. So it's a little bit small, so I hope you could see it. The long one is here, the short one is here. The long one is here, the short one is here. Current flows from the positive terminal, the long one, to the negative. So the current's going down here, current's going up there, current's going up here, and current is going this way for this branch, and it's going this way down for this branch. So again, let's choose one branch to focus on. Let's focus on this branch. So you point your left finger that way, from the north pointing to the south. But can you see my current finger is wrong? My current finger is pointing down. It should be pointing up. So you flip your hand like that. So current is going into the screen, or into that way. You know what I mean? And this is going north to south. What that means, think about it, and if you have to use your calculator in the exam to do this, if this goes down, this thing is going clockwise. Okay, yay, I hope we have it. Let's look at some exam questions. A simplified diagram of an electrical machine is shown below. So we just did this one. That was the first one we did. Yes, it was this one, the first one we did. So is it a DC motor or a DC generator? We said it's a DC motor because of this, the battery. They don't ask why, but DC motor. And I'll just put here that it's because of the battery, that we know that, because of the power source. Write down the energy conversion that takes place while the machine is, and we'll say the energy conversion that takes place is electrical energy to mechanical energy. This is exactly how they ask the questions. Write down the name of component A in the diagram. So A is this thing. A is this thing here. This is a split ring. It's also called a split ring commutator, but you don't have to say the full word. Some accept split ring. Some accept split ring, some accept commutator, but you can say both. But you can just say split ring. Okay, in which direction will the coil rotate? We said it was anti-clockwise. We did that earlier. Okay, let's do another one. I will let you do this one. I'll give you a few minutes. So write down the name of component A. Same thing. This is a split ring or split ring commutator or commutator. State the energy conversion that will take place in the motor. It's the same answer as this one. Which direction will the coil rotate? So who has an idea for that one? I'm seeing different answers. Okay, so we use our left hand. But remember, the first finger that I always figure out that makes a lot of sense is your left. Yeah, I'm sorry. Why am I saying your left finger? That doesn't even make sense. Your magnetic field finger, this one over here. So with that finger, you point from the north to the south. So we're going to be pointing that way with our mother finger. The next thing that is a little bit more tricky to figure out is this, the battery. So it goes from the positive terminal to the negative terminal. So it's going like this, which means it's going that way or that way. I personally will be focusing on this branch. It doesn't matter which branch you focus on, you'll get the same answer. Oh, I love, we have a good debate going in the chat. Some people are saying anti and some people are saying clock. Okay, so from the north to the south. I don't like this because I feel like I have to twist my whole body to do this. I have to point this finger to the south. Then this current finger, remember the third finger is your current finger, I need to point up like that. So I need to point this second finger that way, and I need to point the current finger up like that. That's actually better. There we go. So take a look at the placement of my hand. Okay, my second finger is pointing to the south. My middle finger is pointing that way, like that. What's my thumb doing? My thumb is pointing up. Now be careful, I'm doing it for the pink part of the branch. So what I'm telling you is that the pink part of the branch is going up, okay? The pink part, which is this part, is going up, which means this part of the branch should be going down, which means it should be going clockwise. Let's just check with the other side, this side, to verify. I'm going to look at the other side, the other branch. So you point from the north to the south with your mother finger. In this case, do you see, if I keep my hand like this, my current finger is wrong because here current is going down, but my middle finger here is pointing up. So I need to flip my hand like this. I need to flip it over. Okay, it's a bit awkward, but this mother finger is pointing to the south. This current finger is pointing down. My thumb, you can't see my thumb, it's behind my hand, but my thumb is pointing down. So the green branch is going down. Here's my coil. Green branch is going down. Pink branch is going up. So it's rotating clockwise. Okay. That is not an easy thing to do. That is quite confusing. I did see quite a lot of clockwise. I did see quite a lot of anti-clockwise, but I hope that the more you all practice clockwise and practice with your hands, the better it'll get. I promise you, when we do generators, you'll find generators so easy because we've already done motors, and you'll be like, oh, this is fine. So hopefully the more you practice, it'll become a little bit easier. Okay, and then I didn't show you 9.1.4. States two changes that can be made to the motor for it to rotate faster. So what I would say is use stronger magnets or use a greater current. Name the component that ensures that the coil rotates continuously in one direction. Remember, one direction is direct current. And the thing that makes it a direct current motor is the split ring. Very last one. Let's see if you can figure out if that's clockwise or anti-clockwise. I'll give you a minute. In this one, they're showing you that the current is going this way. Lindo, you have an answer?
It's anti-clockwise.
Anti-clockwise. Finishing off strong. It is anti-clockwise. Beautiful. And great task. Can you see how simple these questions are actually in your paper? So especially for motors, we'll do generators on Monday. They're a little bit more difficult, a little bit, not because of the hand thing or the rules. It's just that you have extra calculations that you need to do and graphs that you need to draw. But yeah, and then write down the energy conversion that takes place while literally the same questions are repeated over and over again. Okay, so any last minute questions before I love and leave you for the week?
Yes, ma'am, I wanted to ask if there's any other way to do the gang signs because my hand is cramping up whenever I point in different directions.
And I feel you. I get the same thing. It's very, very awkward because there's no other way. You just, and it's so awkward in the matric final because when you can see like most people get to this question around the same time and you just start to see like everyone pull up these signs, and then the most nerve-wracking thing is when you think it's a motor, so you use your left hand, but generators uses the right hand, and then you start seeing people around you doing the right hand rule and you're like, yo, so no, there's no other way. You just have to, stretch out those fingers beforehand. It's difficult. I know it's not easy, but hopefully the more you practice, the quicker you'll be able to get it. Because I know holding your fingers like this for long, it makes them cramp up. So the longer you hold it, the worse it's gonna feel. But no other way, unfortunately. You have to use the signs. Any other questions? And then I will see you on Monday.